Germany. In our region, Lower Saxony, close to the border to Netherlands. Okay, I will talk about grid stability and renewable energies with respect to dynamics, turbulent dynamics. I will go in details. As I said, I'm coming from North Germany, from Oldenburg, upper left corner over here. And I'm founding member of the Forwind. It's an organization between a research center of the University Hannover Oldenburg. Without taking the solar energy. This is also contribution. And we are able already to manage the grid in a nation like Germany with up to 60%. Denmark will have up to 100%. France already has sometimes up to 50% wind energy in the grid. And fortunately, it is not going down. But if you read some news, sometimes they have to work a bit more to get the grid stable. My talk will be transition of the grid, what will change. Then I will go in different aspects, power balance, what helps forecasting. I will go in a high frequency, and then the last point, I will go from a physical point of view, discuss the stability of the grid. So the first point, which transition takes place, which we have to face if we come to renewable energies. The electric grid was constructed based on big power centers. In Germany we have 100 gigawatts, so we have around 100, 200 big power centers, which is providing top down the power. And now we are coming in on a lower voltage level with renewable energies, with a big share. And if you look, for example, the map, how the landscape changed, where the wind turbine were installed for 1998 and 2010, you see this energy installation is very much scattered. It's not anymore a few centers and a knot where you insert it, but you have a really broadly distributed region. Down here you would have the similar map for the solar installation. So this will make definitely a totally different collection, organization, how you put the energy together. The aspects of the stability of the grid will be discussed in the third part. But we have to face with this reorganization of the power grid different aspects of stability. There's one, you can define it, the stability from the grid, and this is a nice point, I go in further details. You can define it by the state of the grid you measure at each knot, and this is defined by the voltage, which has 220 volt, plus minus 10% and higher level correspondingly. So the voltage is not fixed, it has a span. We have a frequency which is not fixed, it has a span. And all machines mainly are running synchronously. So we have at each knot a phase angle which tells you whether you're working with the grid or you're out of the phase, which may cause problems. So these are the three aspects, and behind these three aspects it is hidden. Voltage is mainly the power balance. Frequency is a power balance on short term. The frequency will give you the short-term fluctuations of power. And the angle will tell you something about a localized state of one knot. Power, voltage and frequency are more or less global. At the moment we see that the frequency has some local effect if you're high frequency, but if you take the frequency in a minute or in 10 seconds, it is European-wide one and the same frequency. With a transformer with a voltage, you can have different voltages in different grid, but the frequency for all grid parts is the same. Okay. For stabilizing, there are different control schemes. You have primary control, secondary control, tertiary control, not forcium or something, but then the generation schedule. And these control schemes, they depend a bit on the time scales. You have short time, minutes, and hours. And this is naturally, it's growing these different control schemes and different control time horizons, because you have different systems. A nuclear power center, you can't change in seconds. A colleague of mine from the electric engineering is Brunsbüttel. They said the generator were burning, and he claimed that they were trying to make short time power with their nuclear power center, but the whole construction is not constructed in this way. That's why the transformer started burning. I don't know, I cite someone. But usually coal nuclear power center, you change in hours, 5 hours, something. Ramp it up, ramp it down. So this is a totally different control than if you have second fluctuations. Okay, I will go in more details after. Okay, I will start in this sense with the first aspect, the power balance. And for this I will show you that wind and solar power forecasting is a very strong tool, and this is also used at the moment. So you take the weather forecast, and the weather forecast, whether you take the wind speeds or the clouds, the sun expected, you calculate down. You have a lot of methods, weather models. You calculate down for local wind turbines, and then you get in different region where you have installed different wind power. You can see which power is expected, and this information you take for your grid. If you look now at the total grid, you have here the overall of 1 week demand of electrical power characteristic. And there you have quite good models. You have each day at noon a peak, at 6 o'clock at peak. On the weekend you have more, or on holidays you have less power than on other days. So this is typically quite well known. But now you don't have to provide anymore the whole power. This is just some data from our local grid EWE in the northwest. Okay, then you don't provide anymore all power by conventional system, but you have to subtract, or you have to insert somehow the wind energy. So you have the power demand, wind energy, and the rest, the yellow curve, will be now the one which is provided by conventional power system. You have here a problem because you have not anymore a baseline, which we invented for when we built up the nuclear power centers. Nobody wanted to have power in the night, and that's why in the 60s, 70s they started to organize that we have a base line of the power, and then we have short time and the fluctuating one. This was organized in this time, makes sense, but due to the renewable energies, if you come up to 90% renewable energies, you're running in this problem with this concept. And you see, what you need to do now with a conventional power system, it's much more dynamic. But it's important that you can make a forecast. And here, for example, this is a weather model. And from the weather model, you take the calculation of the corresponding local power density. And there you take the characteristic of a power curve, which grows with wind speed to power 3, and which has the rated power and the shutdown. And so you can make here, this is colleagues of mine from Detlef Heinemann, Energiemetrology group. So you have here a wind region, and there you see red is high power. But it's interesting, in the high power, sometimes you get even the high power such blue region with low power. And this was a main problem we had in North Germany, how our center for wind energy was started. It was mainly financed, a good part financed by the electricity company, because if you have high wind, you come over 20 meters per second, you have the shutdown of all wind turbines. And this was the first problem in 2002 when the grid really go down, because they had 100% wind energy in the grid, and with a sudden one farm after the other shut down, and there was nothing. And he had to manage to get the power first out of the grid, second back in the grid to pay it. And then he realized one has to manage it, one has to know it. And with these meteorological tools, you can make the forecast. And if you know, I expect in 1 hour, 2 hours, such a storm front is coming through, you can make your planning. And even can have different way how the turbine's running. You can have high-speed turbines and so on. But there's a probabilistic, state-of-the-art probabilistic wind power forecasting. You take different weather models. You make a mesoscale modeling out of it, and then this is a probabilistic. You have some initial condition, and then you run the weather with different weather system for the next 24, 48 hours. And the important point is, you take your input, your initial condition, you start a variation of it. You make you randomize it, and then you do 50, 100 calculations, which you can now achieve with big computers, and then you get the estimation of the future, what you expect as power or wind speed in the future. And then you get with these ensemble average a prediction with an error bar. And this is important for the energy provider, that they know what is predicted and what is the error. And then in our group, they do it with the observation, a recalibration, and finally the main knowledge they have to take this meteorological data down to a wind farm. You have to take the orographic conditions for this special wind farm into account, and then make good prediction of the wind energy. And there's also from our group 10 years ago a spin-off, a group. They are now 30, 40 people working on it, and they are selling these forecasts to EDF, to all electricity provider. They need the information, and this is a big importance. It is a nice business. So they try, the electricity company try to buy results from independent groups. So each group has its own idea, and so if all forecasting will say, I expect a big wind speed ramp tomorrow, and they are all the same, so they are somehow you can rely on it. But if each model is telling you something else, then you have to take care what is happening and pay attention. Okay, so I'm finished with the first part. This is a voltage, this is a power balance. The power balance, you know, you have the model of the consumer, you have the model of your wind turbine, this is a classic one, and you have to insert as a new quantity what is the expected power of the wind, and you can do the same with solar. And with these together, you make your long-term management, your balance of your demand and production. I come now to the second part, to the short-term control. And this goes into the intermittency and the, fast fluctuating part of the wind energy and solar energy production, as well as the consumption. It is also the consumption if you switch on a demand instrument or a machine, this you make instantaneously. So there's a second reserve, which is finally up to now not controlled by any intelligence. It is only controlled by the inertia of all rotating masses. We have many synchron machines. All power stations are running with synchron machines, and they are running with 50 Hertz. So if you plug in an instrument into the power grid, you will get instantaneously the power, because you can slow down all rotation machines. And if you go off-grid, all machines will speed up. So this part, it is about 1 gigawatt or 2 gigawatt in Europe for a minute or something like this. All this energy is stored in the rotating mass. And that's why the frequency can go up and down. And if you look at your plug here, we can look, if you have afterwards the time, I can show you the video. If you go to the netzfrequenz.de or mainfrequency.com, there you see always the second data of the frequency. And there you see 50 Hertz and how it's going up and down. We have built an experimentalist, so we have built our own frequency measure. We measure it with 10 Hertz, and we see highly fluctuating the frequency. Here's this curve we measured. We took off a kernel. We did decomposing of it to just have the fluctuation. This one is a trading peak, which happens each 2 hours. Yeah, you see when there's a new trading, then some big facilities are switched on or switched off. Each 2 hours you see a big peak, how the market is adapting to the new state of the new trading. So it's nice, you see the trading peaks like you see in the stock market. If you open the stock market at one day, in the morning you always see the depth. This is the, how it's called, adaptation of one stock to the market to the other one. Okay. So we see these fluctuations, and it's amazing. It is fluctuating in 10 Hertz quite a bit. Well, where is this fluctuation coming here from? The fluctuation are definitely coming from the consumers and the providers. If you go in with a new power station, but perhaps this you make a little bit more controlled. But on the other side, this is a point I want to stress. There are new fluctuations coming in due to the renewable energies. And the renewable energies, solar and wind, they will provide, as the wind and the sun is changing all the time, they will provide fluctuations. So just typical figures of the resource, solar and wind energy has about 1 kilowatt per square meter. If you have a sunny day, you get 1 kilowatt. If you have a good windy day, 12 meters per second, you have 1 kilowatt per square meter. You have different efficiencies, 20% and 50% wind turbine. So you get for a wind turbine 500 watt per square meter if you have a good wind. And if you took now a standard wind turbine for offshore, a 5 megawatt, this has 60 meter blades. You get an area of 12,000 square meter. 12,000 square meter would be 12 megawatt, 50%. This is a 6 megawatt, 5 megawatt wind turbine installed. So by the size you can directly see what the turbine is. You see a few days ago, GE built in France the 12 gigawatt. In European project we work on a 20 megawatt wind turbine. I think this will come. To show you the sizes, Airbus 380 has 80 meter span, and this one has 60 meter. So the GE, this has 110 meter. So the GE wind turbine, if it's standing still, the Airbus can fly through, if you have a good pilot. Okay, you can think, this is huge. Yeah, I'm amazed if you, these are huge instruments turning. And they are collecting the energy of this whole area and concentrating in the center. And there it's a transformation. So it's always the argument, the bigger, the more they are smoothing out this fluctuation. But if you look at the power output, and this is a power curve, here's a wind speed, here's a power. The power curve goes with power to the 3, wind speed to power 3. I can explain if somebody wants to know, but it's going up. But then you have a rated power, because at one point you say, I take a 5 megawatt generator, and then I say, here, I do not want to produce more power, because I need a bigger generator, this becomes more costs. So that's typically a 12 meter per second you're cutting now, then you're in the rated power. But if you now look, this is SCADA data, 10-minute average. This is a tradition of metrology, that you always take 10 minutes averages. But if you take now at the second data, and this took quite a long time that I got the second data from a real wind turbine. This is a multi-megawatt wind turbine. And then you see what this turbine is doing during these 10 minutes. It is going nearly to rated power. And it's highly dynamic. In this direction, you see the wind fluctuation. And here, if you are down here, you have more wind than you produce power. So in principle, the system goes up. If you are up down here, you have less wind than power, so the system goes down. So the turbine is nearly shutting down. These fluctuations are the wind fluctuations. These fluctuations are the power fluctuations. So you see it is highly dynamic. It's always, at the end, there will be the best. No, it's running 3 times faster. So, and I take only a part of a few minutes. Yeah? So, you see a jump, and you see jumps in wind turbines of 50% in a few seconds. So you have megawatt changes of wind speed in a few seconds. If I look at a wind farm, and this is interesting, I see 20% of the farm in a few seconds, ramping up and down. I'm working on this. There are interesting effects, synchronization effects, collective effects of the wind park, which in my opinion are all stupid. Stupid. The control system, if I show this, the manufacturers, they say, okay, what the hell, we have to handle this, but they didn't find a better control system. They tried, but there's misunderstanding. Okay, I'm a turbulence research person. I think they must need more about the turbulent fluctuation, what is going on there. And okay, but anyway, they built big machines, and it is quite impressive. But on the other side, 20% of the cost of the wind energy is operation and maintenance. You have nearly all part is failing after 7 to 10 years, gearboxes and so on. And I guess not because they don't know to design it, because they have some loads which are not taken correctly into account. And this load discussion is one of the biggest. Increasing the efficiency, forget it. You make your blade a little bit longer, you have a bigger area, you get the power. But the efficiency, long-lasting, good forecasting wind turbine, this is a challenge, especially offshore. If something breaks, it takes time. But this is a challenge, and to reduce the loads, and this will go directly in the cost. There you have easily 10% costs you can save. Okay, but what is the background behind this? The standard way how you analyze the data, I go a little bit in the data analysis, and there I go into the term, there is a nice poster here on the intermittency. It is very often talked, there is intermittency, but intermittency is in every... It has at least 4 meanings in physics, and in turbulence, and in physics 10 different meanings. So intermittency, if you talk about intermittency, ask the people what they mean with intermittency. But here I show you a bit how... There's a poster. Yes, I know, I refer to it. I refer to it. And then it's very nice what he did, it is just the same way. Okay, 15 minutes, okay, then I have to speed up. Okay, this is standard way how you characterize wind turbines. You take the data, you take 10 minutes wind, you take the turbulence intensity, and that's it. But if you look at such a signal here, you will see you have in a few seconds 10 meter per second change of the wind speed. And these changes are not taken account if you take the mean value and standard deviation. If you go in the increment statistics, if you asks the changes of your variable on a given time horizon. In 2 seconds, how much change do I expect in wind energy or in the wind speed? Then you can characterize this. And if you have such data, you can easily go through the data and make a histogram. How often do you get it? And typically they are plotted the probability in a linear scale, lin. But if you look at the big event, by the way, this is a 10 meter per second change in few seconds. So this is for me a wind gust. If in a few seconds the wind speed is changing by 40 kilometer per hour, this is something how it's speeding up or going down. But wind gust is also, there's no definition of a wind gust. Okay, if you go in double logarithmic scale, you see these are the data, the probability of all events. Here's our biggest wind gust, 10 meter per second. And this is a typical way how you characterize it by norms, by Gaussian statistics. And if you see the difference between the Gaussian statistics, so here you see these extreme jumps, which are in the data. And if you take a probability of a sec sigma event, this would be a change of the wind speed about 5.8 meter per second. I have normalized it to sigma, it is close to 1 meter. So let's say a wind speed change of 6 meter per second in few seconds. The probability is 10 to minus 4. With the data sampling, it is once per day. If you take a Gaussian statistics, you get 10 to minus 10 once per 3,000 years. They don't take this into account. If you take this, and here, this extreme event, you have about the probability a factor 10 you go down, and you have a double of the event. If you go down with a Gaussian, you're here to 10 to minus 30. You're coming at the end of the universe. You don't take this into account. And standard way of handling stabilities, grid stabilities, turbulence of wind turbines to calculate loads are always Gaussian statistics. And therefore you have to understand turbulence. And the point in turbulence is, and this is an essential point, and this is breaking our head in turbulence, this is unsolved problems, this statistics, the shape of the statistics changes with tau. If you understand this, the limit tau against 0, you can solve the Millennium problem, whether the solution is smooth or not of the Navier-Stokes equation. But the statistics, we have a analogy of it, but the rigorous theory of the Navier-Stokes equation is missing. If I look at the power fluctuation, I see the same. If I go solar wind, I have second data. This is my specialty. If I look at the statistics of solar and wind, I see here for 1 second, 10 seconds, 1 minute, I see always the heavy-tailed non-Gaussian statistics with a lot of extreme event in the power. And if you look the difference, now the standard deviation, I take the norm on 1. The standard deviation will change from one turbine to many turbines. There you see some averaging. But in the form, in the extreme events, you don't see it. And if you take a wind turbine or a farm, they nearly have the same statistics. And this is an averaging statistics. It has something. If you look at the solar, you see similar effect. In solar, you have one other. If you're a little bit larger, becoming larger, then you have a cutoff because you have a clear sky. You have 100%. You can't have more. You will see it not so often in a wind turbine that you come really to rated power. They are more fluctuating. But the solar cells, you have this clear sky where you have. Okay. And if you compare solar and wind, you get a nice result. The solar, we take here the 10 minutes for whole Germany. It's not averaging out these statistics. It's even surviving for, if you take whole Ireland or whole Germany, there we have only data on 10-minute scale, synchronously. This is surviving. So this is a background on which we have to organize our power grid on this anomalous statistics. Very interesting if you take the same rated power, solar is much more fluctuating. Solar clouds is turbulence. It's the same nature. But the turbulence make yes and no. They change Langevin noise in jump noise. This goes up. Now you see it at the signal. This is much more jumping, whereas this one is smooth as the wind speed is continuously speeding up. Okay, so this we have to get in the power, and this is mapped. This is controlled out with frequency. And therefore, I look at our frequency measurement, and that's interesting. If I go below 1 second, there I see the heavy tail statistics in the frequency fluctuations over less than 1 second. If I go over 1 second, it's averaging out. It's nicely Gaussian. And if I correlate these heavy tails with the produced wind power, the fed-in wind power, I see a clear correlation between these heavy tails and the wind power. So, but this we are just working. This is just the paper we handed in. I think I get it EPL accepted. But this seems to be a local effect. This is only in a region of several hundred kilometers. We have synchronous measurements in Göttingen, and it seemed to be that the heavy tail we do not see. So this is an interesting point, whether this is in local information for afterwards handling, organizing your grid. You have local information, and then you have to think about what to stabilize you or not. Okay, we are in this point, but now we have the problem. I said we have this rotational mass, which is taking out this fluctuation. But as we increase this part more and more, the rotating mass gets away, and this is a danger. And there's a point, not much attention has been paid in the last 10 years, but now slowly. There are some nuclear power center, Biblis is still running, it's shut down, they just take the inertia. We need the inertia, we are working to get the inertia from the wind turbines, because it has also a rotating machine, but we have an AC-DC AC coupling, so we don't get directly the synchronous machine coupled to the system, but we should do it. We can do it, it's no problem. But one has to be aware of this problem, and then one can manage. Yes, definitely. But it's not done at the moment because you are selling. You have the first right to put it in, and you put the power in, and you don't care about the grid. This is a bit problem. Okay, so I'm done with this one. I run through the grid stability. So the grid stability is also a quite nice, exciting topic picking up in physics, because there's a lot of work on complex network, transport on network. If you take travel, if you take the internet, if you take social interaction, or you take the power grid, these are grids. These are very often just balance, power, transport of quantities. Here you have also the quantity, the power, and the dynamics on it. Okay, the grid is usually here less complex. You have only 2-3 neighbors, not such like these hubs for the airplanes and so on, where you have highly linked nodes. So there's some topological aspects. There is 2 aspects of the dynamics, a static one. This is more or less the capacity of the power lines, whether these power lines get overload or not. And then there's the other aspect, the dynamics. And I will give you a short, some points. Of, for example, for the balance, the power balance, there is a Brace paradox. So if you add a further line, if you enforce one connection, this may destabilize your whole system. And this is a simple argument, because with a sudden you have more power going over, and then you can overload a weak link. This is also known for traffic flows. If you build a freeway, you may cause more blocking than before. If you do it in a stupid way, if you bring the freeway to a point which is weak, and then you overload this weak point. So this is interesting effect. Another point, the dynamics, can show you after the video. The dynamics of the grid is mainly based on a synchronous machines, that they are all phase locked. This is synchronization. If you have different oscillators and lock them, this is a Huygens principle. If you take 2 clocks on a wall, by the knocking, they synchronize. They go perfectly. And this is a nonlinear interaction. And this is known since some time in physics. Exciting field, how a system make phases, make synchronization. And this is a basic principle of the whole power grid, that they synchronize autonomously. And then they are synchronized, but they do not have to be in phase, the same angle. One can run with the angle a little bit ahead. And if you have an angle difference between 2 points, this will tell you then the power flow. So if one is in the head, so you will have, if one, they are connected by a spring. If one is ahead, it is always taking the other one behind. If they are below, it is pushing. Yeah? And this is just the same. If you have a generator here, which is the phase ahead, it is putting energy into, or if it's back, it is pulling out. This is the difference between generator and motor. So these phase differences between these points will determine then the power flow. And you can take the cosine of it, and there you have the dissipation, the losses. But while you have the electrodynamical equations, synchronous machines, you can make, I just showed you before, this balance, that the power is connected between the phase differences between 2 points. But then if you have some power mismatch, what will happen? You will see you will have a frequency changing and speeding up. This is just the equation for the speeding up. This is an electrodynamical equation. And there we have the 3 electricities. So this is a whole, you have this equation. And a common method is to cook all these down to the Kuramoto equation. This is quite long known. These are just coupled oscillators. And these are the models physicists like. And different grids with Kuramoto equation, world grid and so on. There are many, many works on it. And this community is now stepping over to the power grid. Quite interesting. Here you see some chimera and a lot of different effects. But well, here I show you one result. We take the simplified Kuramoto equation with inertia, and then we make a coupling in this way that we take a mean field of all around for 1 knot. So its phase is just a mean frequency, and then you can change the coupling and see if you increase the coupling, you're going up, and with a sudden you will see a transition to phase coupling, that the frequency of your knot is coupled, is 1, is exactly the same as the mean frequency around. But therefore the coupling constant is of importance. This is a coupling between oscillators, and this is a state where you like to have your power grid to be in. Then you can see impact of inertia. If you put in inertia in the grid, then you change here, you have this acceleration term, or you put in a noise, and then you can see how these transitions change. With inertia, you will get hysteresis effects and so on. And here just a simple high voltage global system model, how you calculate the stability of the European grid. You have 1 machine, 1 consumer, and they are coupled by this. And then this oscillation, you give a perturbation on it, and then you look at the phase, the angles, and if you are in an unstable region, you see with a sudden how they start oscillating, how power, this is the Blindleistung, Scheiße, this is always this German word with reactive power. Yeah. The reactive power is flowing forward and backward, and this is blocking the line. Okay, so you can make the calculation of the stability of the grid. There you have the phase where it's stable, the control parameter not stable. And this is interesting because a stable you can take in the physics of nonlinear dynamics as an attractor. And there is a point coming in that this attractor, where you have the bistable case, where you can have synchronous behavior and asynchronous behavior, and there you have basin of attraction, depending on the initial conditions. You are in this state or that state, and there's a problem, this basin of attraction, they have fractal boundaries, and then to determine on this one a stability, it's quite a challenge. And this is known, you need a stability measure for your grid. You know these phenomena, but I want to give a figure and say, okay, is this stable or not? If you add noise, you must see the probability that you stay within and you don't cross the border. Okay, for this we make calculations. We make also calculations here on power grids with noise, and definitely with non-Gaussian noise. And here's the characteristic is, we do the calculation and ask the time it takes that I get a phase change, that the system becomes unstable. That the system, I add here intermittent noise and increase the noise, and then I see when will the system become unstable. And I take the time as a measure because I make probabilistics calculation. I run it again and again and again, and I take the mean time the system stays stable. And this is another measure, not the attractor basin, but the mean time it stays stable with some perturbations. And then you can see, as you increase the intermittency, these mean times will go down. And these are different parameters. But in principle, as you increase intermittency, and this means these tails, these extreme events, definitely, if you have a big jump, one jump is sufficient to kick you out of the system stability. And therefore, you have to know the statistics to say how stable your system is. So if you calculate with Gaussian statistics, you underpredict the stability. That's the point. There is a correction to be taken into account. Now I want to summarize grid stability is somehow my talk. Yeah? There are different aspects. You can have overloads. This is the power balance. You can overloads of one or the other line. This will give you, with a domino effect, perhaps blackout. You have effects that you have phase oscillation between two knots. And this will be reactive power, will cause problems. And this will diminish the capacity of this line, which may cause, with the other one, to a blackout. You have effects that single knots may have different frequencies besides the other one. You have awkward situation where you have this region with one frequency and this, and the one is just a different frequency, and the whole system stays constant, stable, but because it is this one knot which is between two regions, it just adapts. It doesn't make crazy, but it makes another frequency. So such funny states you can see. You can see sensitivity, instability, quite often these end points, knots are quite sensitive to fluctuations, the first one which are kicked out. But you have other topological effect. If you have such branching structure, such knot structure will have another stability than the end one. So and this one, at the moment, many people work with this and try to characterize typical features of instabilities in these grids. And in addition, we have to underlay here the background of a perhaps unknown noise. Okay, so I am at the end. I showed you, I think, these three aspects of the power grid, and I showed you where the renewable energy come in with new aspects. I think quite often with, from the point of a physicist, with exciting physics behind. If you take this forecasting, intermittency, nonlinear dynamics, complex systems, turbulence research. Okay, this is the end of my talk. We have to get smart solutions, neat concept of physics, and here I have a list of publications which I can provide if you're interested. Okay. Game over.
Thank you very much, Joachim, for this beautiful talk. It's open for discussion now.
Klaus Lackner, very, very interesting talk. But one of the questions, particularly the last story about the grid and the beginning story about the non-Gaussian problems at the windmill or solar farm, bring up is the question, how much do you want to load on the grid and how much could you actually smooth things out locally? In other words, distribute the smoothing as well and tie it directly to possibly a single windmill or to a wind farm, and thereby guarantee that whatever enters the grid is stabilized.
If I could give you a good answer, I think I would be rich, or at the end of my research, or I would. No, this is exactly the challenge. And I think, for example, what is very often discussed, but more I think in the literature, that we need big batteries. I showed you the problem of the stability of the grid has different aspects. And I think there is not one solution of it. And we have really to go through. But as you show, we can do the simulations. A problem is still where I'm working the correlation, the coherence of a turbulent field between different points. The averaging shows that there's something non-trivial going on. This to get really in a sophisticated way, I try to make now with sensors in the whole turbulent flow, different measures, and take this little bit the grid system and fit this into the grid to see the realistic turbulent correlation, because the correlations are in wind and solar. And I think these are challenges. But as I showed you, you have different aspects, and this is at the moment we have to work through. We have the capacity, we have smart ideas different, and we have really to go into the problem and see different details. And For the wind turbines on my side, I think the wind turbines, at least in Germany, how it is done, they are driven in a non-adaptive way. They are just selling power and don't care about the system. We can do much, much more with a wind turbine. At the moment, even in a wind farm, each turbine has its own control. Whether you have a turbine in a wind farm or standing alone, it has the same control. They have no collective behavior. And I think this does not go on in the future. You can't just take all your garbage into the grid and say somebody else takes care. And I think the future, if we want to have a future of renewable energies, also the renewable energies have to take care of the whole system. If we provide 60%, we must do something else. And definitely a solution is not wind alone, never. We must always have a mixture. But if you find if you need 10% more battery or 10% less battery, this is tremendous amount of money. It is worth to do the study.
Maybe we'll take 2 or 3 comments.
Okay.
Okay, Stefan Wieland, CES Saclay. If I remember correctly, you showed data on input fluctuations also of solar power, and those were not aggregate statistics, but taken from different sites in the world. And they had more or less the same shape. And I'm surprised by this because I imagine that those fluctuations are governed mostly by cloud patterns that may differ from that may depend on the latitude and also on the ground underneath. And they do not.
Short answer. Perfectly right. I agree with you. In this paper you can read it. Sorry. I expected for wind, I can think it's the same, but the Hawaii data.
I read the paper, and can you make this plausible? No?
You can. Even the data are there. You have the link for all the data. I'm sorry, I don't see big difference. I think if you look more in details, one has to find it. But at this way, as a statistics, at least there's not a fundamental big difference.
I believe the statistics, but is there any physical argument for the same shape?
You have to look at the cloud patterns. I think the cloud patterns, as they are in the shape, are in the everywhere in the world more or less the same.
Okay, fair enough. Thank you.
I claim. I'm not.
Thank you.
Yes, thank you for the presentation. Vincent Mazuric from Schneider Electric. I found 2 differences in your interpretation of the voltage plant at the beginning of the presentation, where you say it's just for equilibrium between offer and demand, and at the end where, and it's my opinion, it's strongly related to the reactive power. Because the voltage plant is related to the resistant torque on each machine, and if you have not the relevant voltage plant, you have a blackout potentially. So this is my first point. And the second one is in your grid, you have always inverters between renewable and the grid. So how do you connect the Kuramoto model or the load flow equation in the presence of inverters?
Yes.
No, it's my question. It's
in inverters or?
Yes, you have inverters. Therefore, you have some wall between the behavior, the physical behavior of the machine, of the renewable machine, and the grid. And if you...
I have not looked at these detailed statistics. I just take the high frequency data and didn't go in the dynamics of the inverters. We are now in a bigger group try to make public resource for grid modeling, because the 2-machine grid modeling you take for the overall supply demand, and we try to make it from a detailed each machine to swing equation, to this one, to Kuramoto equation, to make all the hierarchy down. Because you can't calculate everything, but partially you make it. Because this is, I think, also multi-scale problem. We have somehow to combine these and take all this into account. At some point when you have a problem, it may be your converter, which is the essential part. But at the moment, I did not take all this into account for further work. But you are running, if you take all into account, you can't calculate it anymore. The computer is not large enough. Yes, definitely. I simplified it. I mainly go to the 1-second fluctuations, because there it's not too complicated, it's automatically arranged. If I go a higher fluctuation, other fluctuation, you have to take other effects into account. And definitely one has to. We have this E equation also, and we didn't see big difference between in our models between taking power voltage.
Yeah. So it's José Alois from Non-Renewable Energies. So I have a question about the implicit assumptions in the first part, which I found very interesting. If you want to drive the windmills with weather forecast, you assume that you have enough energy and materials to power the spatial industry and the exascale computing at the same time. Am I right?
Oh, whoa, 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 whoa. I didn't get it perfectly. I have enough power, yeah. No, but it is really amazing. I do this now 20 years. And what you can do now with computation. Okay, we have 300th biggest computer only for wind energy. But what you can do nowadays with computation, it is really big. And definitely for us, it's a challenge. We do all the calculation, highly numerically expensive. And then the point is, out of these big calculations, cook it down, and to get it statistically somehow quite well done that somebody else can do it on the laptop. And this is a part what we do in Fraunhofer also. We try to take this detailed knowledge we are able to detect also for the flow around a wind turbine and then bring it down to simple formulas that you can. And this is definitely a work I think we still have to do the next 10, 20 years, up to the point when we have the new computers, the 3 molecule, 3 atom, 1 atom.
I'm not criticizing the use of it. I'm just noticing that you need it.
Yeah, definitely I need it. I always need non-renewable powers in the future, always. But fossil powers are also renewable. Because it's the sun, it is me.
A good session has to generate some frustration. We'll take just 2 questions and we're out for the count.
Frédéric Wertz, you just say that wind turbines are making some electricity delivering to the grid and the grid cares, which is not optimal. But actors, I heard it already not only for wind turbines but for every producer. Since the European unbundling, producers are just making money out of making electricity and they don't care of the quality of the electricity. Quality of the electricity has to be taken by the TSO. And there is a big debate. The TSO and producer are blaming each other for the degradation of the electricity quality. Could we say that it was a bad idea to unbundling the electricity market, and how can we adapt to get back a good quality of electricity delivered to the grid?
Joachim, just a second. We'll take the second question and then you balance your answers.
And then we can go on with coffee.
For you. Okay. I have a question more out of ignorance probably, but I have heard that you only can have about 35% renewable energy in a system without having a lot of spare capacity in reserve aggregates and so on. So where does Germany get their reserve capacity from? Is it from fossil fuel plants, or are you importing from, say, Sweden that has a lot of hydropower, or where does it come from?
Thank you.
This question, we go on with the coffee. This is a long answer, but you can do it with much more. It's not right, and the statement is not correct. It's definitely always a question of efficiency and optimization. Yeah? But if you take the price nowadays for 1 kilowatt wind hour, it costs 5 cents. If you have spot market oil power plant, you pay 5 cents per kilowatt hour raw oil. You pay 15 cents per kilowatt hour oil, only for the oil, to get 1 kilowatt hour electricity. So you can say it is always commercial to have a wind turbine to save the resource. This will make it cheaper already. So you have to go in details. There's a lot, and this is definitely going in financial models and so on. How much will cost CO2? How much will be our environment? Which value it has, and so on, and so on, and so on, and the quality and so on. But the statement that 30% is the maximum is a statement based on a model. And I doubt that this is the optimal, the last word model. And your question was, I have a short time. I'm short time physicist. Yeah? I like the short time. And memory also. Yeah.
TSO and producer
Yes, no. It is, you're totally right, and I said this is a German market. If you have wind turbines in weaker grids, you have to have other wind turbines, other control systems, other electricity that you take a part of the control of the system. This is, in Germany, the law to start with renewable energies. And there we said we start with, and that's why they have the first right, and they can put everything in, subsidized in such way and so on. Now we are in a position where we have so much power installed that we really have to think it over. And definitely they are commissioned, they are working on it. We won't go on with this capacity. For solar, for example, we have this noon peak. This was the most expensive energy we are producing, where the energy companies make their money with. This is gone because at noon we have solar, an overcapacity of solar. Nowadays the overcapacity is so far, but by the way, the solar still have to pay for this higher price because we don't use it anymore, but we want to have it still. This old contract, it is calculation crazy, but I don't understand. But now it's a peak so high that each solar cell modern must have the capacity to reduce by 20% its power. Yeah, this is just such. We have, if we are growing up with a capacity, we have to think it over. It is needed, and this is my message. We need clever, not stupid. It's most stupid. We pay negative price for energy, for wind energy. Instead of shutting down a wind turbine, I can calculate what power was lost. We pay negative prices for it to sell it, because Germany we have the problem. Last comment. Germany we have the problem. This is a citation of our CEO of the electricity company in Ostfriesland, EWE. All Vattenfall, RWE, and so on, ENBW, they just went on business as usual the last 20 years. And this way we have a total overproduction of power. We have coal power plants, we have gas power plants, all built, they are not running. Because nobody took into account that we have grown renewable energies. And this causes a problem. Our CEO said, usually if you build a car which is totally off the market, you will make bankrupt. But now we put money into all these companies because they are partially state-owned and subsidized and go on. Now we must have clever solutions. Energy is something our whole life is based on. We have to take the best profit of it. And therefore we need clever, and the young generation, new ideas to get in to manage it. Okay, yeah. Thanks.
Thank you. So now, a little bit of a slice of poster session, and then we're back here at 10:45 sharp.